All right. Well, welcome, guys. Today we're going to look at a lesson in chemistry that is very important and a complicated one at that. So I'm back here in the Sadness Cave, as I like to call it. This is my office at home, and I haven't had to teach here in quite some time. So, you know, get excited about that. But we are going to get going here, and the way we're going to do that is remotely. So I'm going to teach the lesson here like this, and I want you to copy along. At various points I'm going to say, hey, now would be a good time to pause and work on this. Please actually, let's pause the video in class and have you work on it, alright? I know this isn't an ideal way to learn a complicated topic, and this is a complicated topic. There's no getting around it. But we're going to do our best, we're going to work together, and be aware that you don't have to understand this all in one day. We're going to do this a bunch, alright? We're going to talk about this several times over the course of this semester and get there. So, over the last bunch of days, you looked at Lewis structures. And when you're looking at Lewis structures, we looked at kind of the rules we wanted to follow and how we were going to draw them. So let's do that again, and we're going to do it for one that we've done a bunch of times already, which is methane. So you've got your note here in front of you, lesson 1.5, bonding, day 2. Let's take a look. So here we are. And now that we've got that, draw a Lewis structure for methane, CH4. Of course, that should say CH4. But these are the minor details. Okay, let's do this. Well, we know the rules, which is the first thing we want to do is count. So here we are, we'll count, and we'll say carbon should give us 4 valence electrons, and hydrogen should give us 4 valence electrons. There's no charge, so that's a total of 8 electrons. And then we put the least electronegative atom in the center. So we're going to put carbon in the center, and we're going to surround it with a hydrogen on each side, just like that. And once we've done that, well, we can draw a bond here, a bond there, a bond there, and a bond there. And now we can count electrons. And we have 2, 4, 6, 8. And we're supposed to have 2, 4, 6, 8. So that's the structure. And it works. Because each hydrogen has 2 electrons around it, which is what we want. And the only carbon has 8 electrons around it, which is what it wants. So we can kind of look at that and say, great, that's the structure. But we're going to look at 2 reasons why that actually can't be the structure. So we'll talk about 2 of them in a row. The first thing I want to do is look at the electron configuration. Alright, let's look at the electron configuration. And hydrogen's electron configuration we'll put over here, and carbon's electron configuration we'll put over there. And what we're going to see is, how do the electrons actually pair up for this bond to happen? Let's take a look. So hydrogen's easy. It has 1 electron. So in its 1s orbital, it has got 1 electron. And I'm going to draw that a different color just so it really stands out. Okay, there we go. In its 1s orbital, we've got 1 electron. Now, carbon has a full 1s, so it's got 2 electrons in 1s, and then it has got 4 electrons in its valence, which means 2s is going to get 2 electrons, and 2p is going to get 2 electrons, and of course they should go in according to Hund's rule, like that and like that. So hopefully that makes sense to you. If that doesn't make sense to you, you've got to go back and relook at our lessons on electron configurations, not the quantum rule. But all we've done there is just put the electrons where they go. Now, here's the issue. We're going to see two reasons why CH4 shouldn't really be possible. Because these have to share electrons to complete orbitals. So the first pairing with the first hydrogen would be easy enough. But keep in mind, we've got 4 hydrogens, right? So the first hydrogen has a 1s, the second hydrogen has a 1s, and the fourth hydrogen has a 1s. And I'm going to use blue for that, and I'm going to use green for that, and I'm going to use, oh, I don't know, purple for that. Great, there we go. So the problem is this. When they go to bond, one moment please, guys. Guys, you really can't be vacuuming, please. It's okay. Yeah, no worries. It's okay. That's fine. Thank you. Love you all. Okay. Sorry about that. Like I said, welcome to the sadness cave. This was COVID life for me for like a full year. Anytime the furnace goes on, anytime laundry needs to be done, and anytime the vacuum goes. Anyway, okay. So now, this bond here, well, that could be this electron pairing up with that electron, being a shared pair. Great. And then this bond here, well, that could maybe be this electron pairing up with that electron. But the problem is now, how would I form this bond here? See, the problem with there is, when I go to share this electron, I can't share it here because they're already paired up. And I can't pair it here because that orbital is empty. So we have a problem. And the problem is, this can't share because it's full already. And this can't share because it's empty. And keep in mind that every time we share electrons, it has to be an equal sharing. Each atom has to donate 1 electron, and that becomes a shared pair. You can't have both of them coming from one. So, the problem is carbon, even though we know it makes 4 bonds, if we look at its atomic structure, it can't make 4 bonds. So what happens? Well, scientists thought what might happen, and this is close, is that this electron might get promoted into that orbital. And then we would have 4 orbitals that weren't full and ready to share. The problem is that that can't happen because this orbital is a lower energy orbital than that one, and the off-bow principle tells us that lower energy orbitals always get filled first. So these orbitals don't work. So the atom has to make, wait for it, new orbitals. And there's another piece of evidence for this, which is the shape. If you look at the shape of p orbitals, and I'm going to pull that up for you here. I have here, sorry, it's just loading up, the shape of p orbitals in 3 dimensions. And if you look, here they are. Oh, of course it has immediately stopped loading, as will happen. There we are. If we look at p orbitals, you can see that they are at 90 degrees to each other. There's one of them, and there's the next one, and there's the next one. P orbitals exist at 90 degrees to each other. And if we spread out, if we look at 2p orbitals, same thing, 90 degrees to each other. So p orbitals exist at 90 degrees to each other. So if the bonding were happening in p orbitals, we would expect all of the bond angles to be at 90 degrees to each other. But scientists are able to actually see the 3D shapes of molecules. They use a process called X-ray crystallography. It's really cool. You can take a crystallized form of a compound, and if you shoot X-rays through it, you get a pattern that develops on the X-ray film that actually gives you, if you know how to decode it, the shape of the object you're looking at in 3 dimensions. And if we actually look at the shape of methane, of CH4, well, if we look here, I'm going to zoom in. This is CH4, and you may not be able to tell, but these are not at 90 degrees to each other. They're not at 90 degrees to each other. In fact, I should be able to measure the angle. Sorry about that. But if you measure the angle, it's going to be about 109.5 degrees. Of course, this no longer wants to run, which is very frustrating for me, but that's okay. I'm just going to close that. So anyway, we can say 2 things. The orbitals can't exist like this, so we need to have different orbitals than just s and p orbitals. Because p orbitals are at 90 degrees to each other. We can see that this has to happen with s and p orbitals, but s and p orbitals don't work in shape. Also, the way it stands, that full s orbital is a problem because it can't share because it's already full. And that empty third p orbital is a problem. It can't share because it's empty. So, we need to make a new orbital. And how we make a new orbital is what we call a hybrid orbital, where when an atom is going to bond, the electrons in the s and the p of the valence have to go from being at slightly different energy levels, with the s being lower energy level, so filled first, and they have to be made so they're all the same. And the way they do that is the s orbitals and the p orbitals blend, or they do what we call hybridizing. They make a hybrid. So, oh gosh, what did I just do? Whoops. There we go. Because of carbon's electron configuration, it only has 2 electrons it can share. And I gave you the symbols of them here, but it's this one and this one. So even though it needs to make 4 bonds, carbon can only make 2 bonds in this configuration. So the orbitals have to change. All of the valence orbitals, in this case the 2s and the 2p orbitals, come together to make new orbitals called hybrid orbitals. So this is what happens with carbon. Carbon before is going to become carbon after. So before we had, and I'm just going to draw the 2 level, we had 2s with 2 electrons in it, and then we had 2p, and it had 2 electrons in it. And what is going to happen, 2 electrons, what's going to happen is that these orbitals here will join to form hybrid orbitals, to come together. And so after that, after they have joined, we will get what we call a 2, because it's still energy level 2, sp3 hybrid orbital. And this name, we would say sp3, and it means that one s orbital, I'm going to use the word 1 so we know I'm just counting, one s orbital and 3 p orbitals came together. And that means we're going to have 1, 2, 3, 4 orbitals here, because we had 1, 2, 3, 4 orbitals there. So the 4 old orbitals become 4 new orbitals, but importantly now they all have the same energy level. And because they all have the same energy level, the electrons will fill first one, then another, then another, then another, and now each of these is ready to make a sigma bond. And that means that if we go back and look, it means that now this electron here, hydrogen's electron, can go there. And this electron can go there. And that electron can go there. And that electron can go there. And now we can form the 4 bonds we need to form. So by forming hybrid orbitals, the atom is able to make orbitals that are ready to make sigma bonds, ready to make bonds. So, weird to think about again, but because the electron configuration doesn't work because that s orbital gets filled, which leaves one of the p orbitals empty, carbon has to put those together and make an sp3 hybrid orbital. Awesome. Okay. And that's going to happen anytime you need to make a sigma bond. That's going to be a little rule. It already says that there, but we're going to say it ourselves anyway. Sigma bonds will always form and only form in hybrid orbitals. The only exception to that is hydrogen, because it's in the first shell and it's just a 1s orbital. But for anything other than hydrogen, sigma bonds will always and only form in hybrid orbitals. So carbon has to do what we call hybridize its orbitals to make any sigma bonds. Okay. Again, listen to me. I know this is a little confusing. I know it's a little tricky. Don't worry. You know what we're going to do tomorrow? Go over all this stuff again. So just bear with me, get the note down, and trust me, please trust me, that with a bit of practice, this will come to you. I promise. Okay, now, that's great that if we have sigma bonds, anytime we have single bonds, they're going to have to go in a hybrid orbital. Let's look at a case where we don't just have single bonds, we also have some electrons that aren't shared, what we call lone pairs of electrons. So let's draw a Lewis structure of water, and I'd like you to pause the video at this point and actually take the time and draw the Lewis structure of water using the rules. Pause. All right, I'm going to assume we're back. So given that we're back, let's draw that Lewis structure together, shall we? Okay, so Lewis structure of water, well, we're going to count, and we know that 2 hydrogens are going to give us 2 electrons, and we know that oxygen gives us 6 electrons. There's no charge, so we have a total of 8 electrons. Cool. All right, let's do it. So we put the central atom, which in this case is the oxygen. I know usually we put the least electronegative atom in the center, but you can't put hydrogen in the center because it only has one measly little electron. So there we go. And we put a single bond between them, and now we'd count. And we only have 2 4 electrons, but we need to have 8. So we know we add lone pairs. So we're going to add a lone pair here and a lone pair there. And that should be the structure of water. So now let's take a quick look, and we know that that is a sigma bond. We know that is a sigma bond. But we know this is a lone pair. And we know that is a lone pair. Okay. So there we go. Now, let's take a look at the electron configuration of water. Well, there it is. So again, we don't have to worry about the hydrogen. Let's look at the electron configuration of the oxygen. So I'd like you to pause the video again and write out the electron configuration of oxygen, and then we'll take a look at it. Okay, well, oxygen will start with a 1s, and that 1s is going to have 2 electrons in it, just like that. Great. And then we're going to have 2s, and it's going to have 2 electrons, because in the valence, in the second shell, oxygen has 6. So then we have 2p, and it's got 1, 2, 3, and we've got to put 4 more electrons here. So it'll be 1, 2, 3, 4. Okay, so the problem is, these, you could say, well, we've got a lone pair and a lone pair, and we've got this ready to make a bond and that ready to make a bond. Isn't this perfect? And it would be perfect, except sigma bonds will always and only form in hybrid orbitals. Sigma bonds will always and only form in hybrid orbitals, and we can prove it because, coming back to that angle, if it was a p orbital that this was happening in, if it was 2 p orbitals, then the angles would have to be at 90 degrees to each other, because p orbitals are always at 90 degrees to each other. But if we look at water, again, if we do the X-ray crystallography thing, and we look at water, we're going to see that water does not form at 90-degree angles. In fact, water's got this really specific angle that we'll talk about in our next full lesson, but that is not 90 degrees. And I'm going to try and try this out. There's our JMOL model. Doesn't that look pretty? And I'm going to try to get the angle on it, and watch. $104, not 90 degrees, but 104 degrees. So that can't be a p orbital. So the problem is p orbitals can't make bonds. Sigma bonds don't make sigma bonds. So even though there are 2 p orbitals with only 1 electron, hybridization still happens. The angles prove that to us. So we still hybridize, which means that this old arrangement, 2s and 2p, looking like that, just what we had above, is going to form hybrid orbitals. And again, what would we call those? Well, we're in the second shell. So we're going to say we're in the second shell. And then what did we put into them to make the hybrids? Well, we put the s orbital, so 2s. And then we put how many p orbitals? 1, 2, 3. So we're going to call it sp3 hybridization. 2sp3 hybrids. And how many of them are there? Well, since it's an s and 3 p's, altogether that's 1, 2, 3, 4 orbitals. And now we have 1, 2, 3, 4, 5, 6 electrons to put in. 1, 2, 3, 4, 5, 6. And you'll see then that this is a lone pair. And you'll see that this, did I use purple? Yeah. That is a sigma bond. And that is a sigma bond. All right, and when hydrogen comes along, hydrogen's 1s here, that and that will come together and form a bond. So that is where the sigma bonding happens. Okay, so that seems a little confusing. Totally understand it's a little confusing. It is a little confusing. We're going to get this with practice. Trust me. Do you trust me? I hope you trust me. In any case, the rule we take away from this is that sigma bonds, and we said this above, will always need hybrid orbitals. Unshared electrons also go in hybrid orbitals. All right, so once something bonds, the unshared pairs also go in hybrid orbitals. So even if you're going to have some unshared electrons, that hybridization is still going to happen. Those orbitals have to come together. Now, why talk about this at all if everything goes in a hybrid orbital? Well, the answer is there's one thing that doesn't go in a hybrid orbital, and that's what we're going to learn about next. We call those, well, the other kind of bond. Sigma bonds go in hybrid orbitals, but pi bonds don't go in hybrid orbitals. So we're going to take a look at the nitrite ion, NO2 with a -1 charge. So again, we'll start with a Lewis diagram, pause this video, draw a Lewis diagram. Okay, I'll assume you've done that. Let's count. We've got nitrogen, which gives us 5 electrons. We've got 2 oxygens, which should give us 12 electrons. And we've got a -1 charge, which gives us 1 electron for a total of 18 electrons. All right, so we're going to draw nitrite. Again, assuming you've done this, so I'll go quickly. We put nitrogen in the center, and we're going to draw 2 single bonds to oxygen. And then we're going to complete the octets of everything around. So 1, 2, 3, 4, 5, 6. Another pair here, another pair there, and another pair there. And if we count quickly, that's 8 electrons. That brings us up to 16, but we need 18. So we need another pair of electrons. And where do we put that extra pair of electrons? That's right, they go in the center atom. So they would go right here. And we're not done because nitrogen still doesn't have 8. Nitrogen only has 6. So we're going to have to take this pair of electrons and turn that into a bond. Make that a shared pair. And I'm going to draw that with this blue line because, if you recall, we said that's a sigma bond. That's a sigma bond. That's an unshared pair. But this is what we call a pi bond. And you might have wondered why we bothered giving these different names. Well, we give them different names because it turns out that they form differently. Now, if you remember, when we looked at the shape of water, we got this bent shape at a certain angle. As we'll learn tomorrow, we get a different angle from this, which tells us something, actually. I'm not going to get into it too much yet, but let's just take a look. What it turns out is this. You'll see that nitrite has 2 sigma bonds and 1 unshared pair of electrons. And I should have said on this, talking about the nitrogen. We're talking about the central atom. This will require 3 hybrid orbitals, but the pi bond does not require a hybrid orbital. A pi bond has to be made from a p or a d orbital. Pi bonds cannot go in hybrid orbitals. They don't, as it turns out, ever go in s orbitals. they have to come from a p orbital, or later on, we're not there yet, a d orbital. So, what's that look like? Well, let's talk about nitrogen. Nitrogen's default electron configuration. Draw it. We'll pause this video, draw nitrogen's electron configuration. All right. Hopefully you've unpaused it. Nitrogen at its 1s has two electrons, a full shell, and then its second shell it's got 5 electrons. So that means a full 2s, and then 2p with 3 more electrons. That looks like this. 1, 2, 3. Now you might be tempted to say, well, that's perfect. We've got our unshared pair, and we've got 3 bonds ready to go. Isn't that what nitrogen's making? But 2 rules. First rule, sigma bonds need to be in hybrid orbitals. Unshared pairs need to go in hybrid orbitals. But we can put our third rule here. Pi bonds do not go in hybrid orbitals. Which means when we go to make this, we're going to need 3 hybrid orbitals and 1 regular p orbital. Three hybrid orbitals and 1 regular p orbital. And so what happens is that these here are going to hybridize, but this one right here is going to stay a p orbital. Which means we end up with something that looks like this. We still have 1s, obviously, still got 2 electrons in it, but then at level 2, we now have a hybrid orbital. And just like above, we're going to call it an sp hybrid. Now here we called it sp3, because it was made from an s, and then 1, 2, 3 p orbitals. But here, we're not using 3 p orbitals. It's made from an s orbital, and then 1, 2 p orbitals. So we're going to call it